Hi. Today I will talk about, in this lecture, I will talk about homomorphisms of rings. And ideals. Okay, so do you remember for a group, if we have two groups, let's say G and H, then a function from G to H is a homomorphism for a group's homomorphism. Remember, if f of x, y is equal to f of x times f of y for all x, y in G, namely f maps the operation of G into the operation of H in some sense. Okay. For the rings, it is similar, but in the rings we have two operations, so that function should preserve these two operations. So for this, so let R and S be two rings, and f R to S be a function. F is called ring homomorphism. Or just a homomorphism, if it preserves these operations, namely f of x plus y is f of x plus f of y, and f of xy is equal to f of x times f of y. So for all x, y in R. So here, this operation addition is the addition in the ring R, and this is the addition in the ring S. And that's the multiplication in R. This is the multiplication in S here. Okay. So as in the group theory, this F is called a homomorphism. F is called a monomorphism. If it is one-to-one, and F is called an epimorphism if it is onto, and F is called an isomorphism of course. F is a homomorphism here, isomorphism if it is one-to-one and onto. So in this case, if F is an isomorphism, so here's an exercise for you. If F R to S is an isomorphism, so that it is one-to-one and onto, so that then the F inverse is a function from S to R. So since it is one-to-one and onto, it has an inverse. This is also a homomorphism, an isomorphism. Since F inverse is one-to-one and onto, you just need to show that it is a homomorphism. So you need to show that it is a homomorphism. Okay. And if there is an isomorphism like this, if there is an isomorphism, there is an isomorphism F from R to S. We say that R is isomorphic to S. S and write like this: R is isomorphic to S. So let's use this notation. And now suppose let F from R to S be a homomorphism, be a ring homomorphism. Then we can look at the elements mapping to the zero, namely that is F inverse of 0, or it's the same thing as X is in R, such that F of X is equal to 0. This is a subset of R. This is called the kernel of F. It's called the kernel of F. And the image of F is, as usual, let's denote it like that. It is the set of all F of X such that X is in R. So that this is a subset of S. So here's an example of this kernel of F. Of course, when F is a homomorphism, kernel of F and the image of F are subrings. Namely, kernel of F is a subring of R, and the image of F is a subring of S. So remember, in order to check that if we have a subset, let's say H is a subset of R, in order to check that this is a subring, we need to show that for every X, Y in H, X minus Y is in H, and X plus Y, X times Y is in H. So that we proved last time. This is a subring if and only if these two conditions are satisfied. And let's check this. Let's say, so let's show that kernel of F is a subring of R. So of course, this kernel of F is never 0, is never empty. You can check this, that F of 0 is always 0. So let's check this. F of 0 is equal to 0. So F of 0, well, in group theory, you know this, but let's do it once again. F of 0 plus 0 is F of 0. This is F of 0, by the way. F of 0 plus F of 0. If you cancel these F of 0s from both sides, you get cancel, because in the abelian group, you add the inverse of F of 0 to both sides, and you get F of 0 is equal to 0. So that this 0 is always, 0 of R is always in the kernel of F. So let X and Y be two elements in the kernel of F, so that F of X is equal to 0 and F of y is equal to 0. And let's show that their difference is also in the kernel. So remember, x minus y means fx plus minus y. And since f is a homomorphism, this is f of x plus f of minus y. And since f is a group homomorphism from R to S with the if you just consider the addition, so it's a group homomorphism, so that this minus sign goes out. So it is f of x minus f of y. So that, and this is f of x is 0, and f of y is 0, and the difference is 0, so that x minus y maps to 0 by f, so that x minus y is in the kernel of f. So this first condition is satisfied. In order to check that it's a subring, the first condition is satisfied. Second, I said, so let's look at f of x times y. This is, since f is a ring homomorphism, this is f of x times f of y. But f of x is equal to 0, since x is in the kernel, times 0. And that's 0. 0 times 0 is 0. So that means x times y is also in the kernel of f. Therefore, kernel of f is a subring of R, because of these two conditions are satisfied. It's a subring. I will leave this image of f so that it's a subring of S. Yeah, I will leave this to you as an exercise. I urge you to do that. So this kernel of f satisfies one more property. One more property. Namely, so remember, if x is in the kernel, y is in the kernel of f, then x times y is in the kernel of f, as we just showed above. But more is true. So if let x be in kernel of f, and kernel of f, and R be arbitrary element in R. So if you look at f of x times R, that is, so this is in the kernel, x is in the kernel, and R is in R. So it is f of x times f of R, and f of x is 0 times f of R, and we showed that 0 times any element is 0, so that x times R is in the kernel of f. And also, if you look at f of R times x, this is f of R, f of x, and f of x is 0, so that it is f of R times 0. This is 0, so that also R times x is also in the kernel of f. And so more than subring, more than just a subring, this condition is also satisfied. And we make this definition. So let I be a subring, be a subset, non-empty subset, non-empty subset of a ring R. We say that I is a left ideal if these two conditions are satisfied. X minus y is in I for all x, y is in I, and also x times r times x is in I for all x in I and for all r in R. So this is called, we said I is a left ideal if these two conditions are satisfied, and I is called right ideal. If these two are satisfied, namely this first condition is the same for all x, y is in I, and the second is that x times r is in, when you multiply x from the right hand side, it should be also in I for all x in I and for all r in R as well. And we say that I is an ideal. Usually we will just say ideal. Ideal if it is both, it is left and right ideal. Namely, in order to show that an I is an ideal, you need to show that x minus y is in I, or if x, y is in I, and also x times x, x times r should be in x for all x in I and for all r in R. So if these two conditions, here there are two elements, are satisfied, then we say that it's an ideal, both left and both right ideal. So therefore, so we showed about that if F is a homomorphism, this is a homomorphism, then the kernel of F is an ideal, as we just showed that above. So remember, in the group theory, if you have a group homomorphism, its kernel is a normal subgroup. Here, the kernel is an ideal. So that so in groups we have normal subgroup, and in rings we have ideals. So ideals correspond to normal subgroups, and the subgroup in some sense corresponds to subring. Okay, in some sense it's like that. Okay, next. So here's an exercise for you. You should do them. You should do that exercise. I will do one of them. First one is, so let I and J be two ideals of R, of a ring R. Then this intersection is an ideal. Is an ideal. So in general, more generally, if this I of alpha, where alpha runs over some index set, is a family of ideals, in R, then their intersection is an ideal. An intersection of all these ideals, where alpha is in this lambda set, index at lambda, this set is an ideal. The intersection is an ideal. So namely, this is the intersection of all I of alpha such that alpha is in lambda. So union in general is not an ideal, but intersection is an ideal. What else? Okay, here's a solution. Let's solve this one. So let I be this intersection. I be the intersection of these all I alpha such that alpha is in lambda. Then, so of course, 0 is in I alpha for every alpha, so that 0 is in the intersection of I alphas. So that's in I. So that I is not empty. I is not empty. So let X and Y be in I, so that X and Y are in the intersection of intersection of I of alpha. So that means X and Y is in I alpha for every alpha. But I alpha is an ideal. So that means X minus Y is in I alpha, and XR and RX are in alpha for all alpha in lambda and for all R in R. So that means so since for every alpha this X minus Y is in alpha, so that I alpha X minus Y is in the intersection of all I alphas. Namely, that's I, and also X R and Rx is in I, so that so therefore this I is an ideal. The intersection is an ideal. Okay, the intersection of any family of ideals is an ideal. So in the first part, in one, we had only two ideals. In particular, for finitely many of them is two, and in three, so in general, I union J is not an ideal. And so here is an exercise for you. So let I, J be ideals, suppose, in R. Then look at this I plus J. I plus J is A plus, let's say X plus Y. X plus Y's it consists of X plus Y such that X is in I and Y is in J. This is an ideal. So that's an ideal. Okay, so I will leave this to you. Next, so one more thing, exercise, example of an ideal, most important example. Let's take R to be Z integers, and let's say I to be n times Z, where n is some positive integer, some positive integer. So n times Z, remember this is n times Z is n times k such that k is integer. So that it is, it consists of 0, let's write like this, 0 plus minus n plus minus 2n plus minus 3n, etc. So all these, so let x and y be in I. So this is not empty, of course, I is not empty. Then x is, we can write x as, and also let's say R be in R. namely R is an integer. R is an integer. So that since x is in I, so we can write x as some n times k1. Let's say k, n times k, and y is n times l. So that x, let's look at x minus y. It is n times k minus n times l, but it is n times k minus l. So this k minus l is an integer, so that this is in nz, namely it's in I. So that the first condition is satisfied above, in order to check the first condition of being an ideal. So this is the first. Second is, well, let's say x times r. What's x? Well, of course, it is r times x. This is abelian, so that both of them, they're equal. And r times x is n times k. It is the multiple of r times k. This is an integer again, so that this is an n times z. So therefore, n times z is an ideal. I is equal to n times z is an ideal of z. That's an ideal of z. Also, yes. And so here is another example, or better, not example, but non-example. Non-example. So, of course, every ring is an ideal in itself. So let's take R to be the real numbers or rational numbers, and I to be the integers, and the I is a subring, of course, subring of Q. But let's see whether it is an ideal. So, for example, 2 is in I, and let's take 1/3 from Q. So if we multiply them, 1/3 times 2, which is 2/3, is not in Z, so that this Z is not an ideal. Z is not an ideal. One more example. Yeah. So let R be a ring again. You should check that there's 0 and R itself are ideals. They are trivial ideals. Ideals. Okay, they're ideals. Okay, now since R with the addition, so R with the addition is an abelian group, we can look at and I with this addition is a subgroup, or so that it's a normal subgroup. So in an abelian group, every subgroup is normal. Every subgroup is normal. So we can look at the left cosets of I. So it is x plus i's left cosets, such that x is in x is in R. Okay, so we look at the set of left cosets or cosets, and let's define. So this is the set of cosets or left cosets. Left cosets and right cosets are the same. So let's define an addition and multiplication on R over I as follows. So if you take two elements x plus I and y plus I. Let's define this addition to be in a natural way, x plus I plus I. So the left coset of x plus I, and let's define multiplication also. X plus I times y plus I to be x times y plus I. Of course, so that here x plus I can be can be represented by also by r. For example, this is true if and only if x minus r is in I. Remember from the group theory. So that if, for example, if x is in I, so that x plus I, we just, or that's 0. Since x minus 0 is equal to x, 0 plus I, that's also I. That's equal to I. Okay, this is side information. So we defined the addition and multiplication this way, but there's a problem. The problem is that these are well defined. These are well defined. We need to show that they are well defined. So how do we show that? Well defined. So so suppose x plus I, this left coset is also represented by r plus I, and y plus I is also represented by s. So that let's see, we need to show that x plus I, the left coset of x plus I is equal to left coset of r plus s. R plus s. So we need to show this, so that since because of this x minus r is in I, because of this y minus s is in I, so therefore x plus y minus r plus s, which is x minus s r plus x minus r plus y minus s. This is in I, that's in I, so that's in I. So that means x plus I, x plus y, the left coset of x plus y is equal to left coset of r plus s. Namely, the addition is well defined. Addition is well defined. And let's look at multiplication. For the multiplication, xy minus, so we need to show that x times y plus I is equal to r times s plus I. Well, let's show this. Let's look at this rs. If you add subtract first, subtract x times s and add x times s minus rs. So I did not do anything. So if you factor out x from here, it is y minus s. And if you factor out s from here, x minus r is in times s. So this is in I. That's in I. This is also in I. So since this is in I, everything is in I. So that the result, and similarly this gadget is in I. So that the sum, everything is in I. So therefore, so that x y minus rs is in I. So that xy, the left coset of xi and the left coset of rs are the same. So that here the multiplication is well defined. So here we show that addition is well defined. In our left coset, we define two operations like this, and we show that these operations are well defined. And I will leave as an exercise to you, show that this R over I with these additions and multiplications is a ring. It is called a quotient ring. Quotient ring, and also if you define from R to R over I by taking x to x plus I, the left coset of I, is an epimorphism. So it's a homomorphism which is onto. So that's an epimorphism. Okay. I guess my time is up, almost more than 35 minutes. So I will finish here. In the next lecture, I will start with isomorphism theorems. Okay, bye.